recording, and then I will share my screen just to get us started. So this is welcome everybody again to another series of CONGA meeting. As we know, CONGA is a network of ground-based instruments, like continuous network of GNSS receiver. And we always come here every last Wednesday of the month to educate and to get to know people who we can work with. And when the time comes to put receivers across the equatorial region of Africa, as we know, the equatorial region of Africa, as shown in this photo here, has been a desert kind of when you talk in terms of instruments, there are spice, GNSS or ground-based instruments around this region. That is why we are very, very interested in this region. Not only that, science, equatorial dynamics and low-latitude dynamics are essential. As you can see from South America, the map of South America shows the opposite. You can see how TC results and the equatorial ionization anomaly is well defined on this region. And if you look at the same region of Africa, you can see we can hardly see the EIA here. So we are very much interested in putting instruments, all kinds of ground-based instruments, but particularly we are focusing on GNSS receivers at the moment. So at the time, we are proposing this GNSS receiver at the bottom here. And all of these locations have been, they are either higher institutions or colleges. So these are not just anywhere. They are specific locations that we have we have uh, assigned or allocate in this map. So today we have the privilege to have a very august visitor. I won't call him a visitor because we actually started this um, mission, Conga mission together. It was parcel of this initiative. At the time we are commencing, we started this. So Dr. Cesar is a well-known senior scientist, and as you know, or you may know, is the PI of NISN. And NISN is a kind of network distribution over South America. And he has been doing this, overseeing this network for a very long time. You will hear a little bit more about that with him. And by the time, I think we will come back for other things. So if we have the time, I will just give us the room to meet some of our people that are joining us for the first time. But before we get into that, I think we should give Dr. Cesar the chance to talk to us this morning on, let me see, what is the topic? That is the future of NISN. That is low latitude ionospheric network
Sensor
station
network.
sensors network. Yes, thank you. And it's used to understand N1K irregularity. So N1K irregularity will be discussed, and I think Dr. Cesar, I will give you the floor so you can take over from here. Thank you, Dr. Cesar, for granting our request to educate us this morning. You may share. Okay, good.
Well, thank you, Jonah, for the nice words. No, thank you for inviting me. Good morning to everybody, or good afternoon, probably, in some places. Let me go to the full screen.
Thank
Okay.
you. Yeah.
Yeah, I'm working now for Boston College. I came back a few months ago. Yeah, it's my pleasure to talk to you about LISN, how LISN is getting transformed in another acronym that we call forward. Yeah, so I'm going to tell you this, but I'm going to also to mention two projects I'm working on. No, these are investigations, and probably that can be done also in Africa, in other parts of the world, by the way. As you can see on your right side, these are data from ionosomes. No, and I'm going to be talking about also about ionosomes, not only GPS receivers. What you see here is data from Huancayo in Peru. That was taken in 1960. In that time, it was a new ionosome that working. The ionogram at the top, you can see that it has a range spread F. Many of you are familiar with that. So range spread F is due to the plasma bubbles when they drift. So there is this spreading range, which is altitude, in other words. No, well, I'm not going to go into details, but the one at the bottom here is called frequency spread F, which is more than spreading frequency, which is related to the density. So, and that has to do with the last topic that I'm going to be talking about. Now, on your left, this is the anomaly, but it looks very atypical. No, this is not doesn't happen very often. No, but sometimes we see it. No, and we see even more very strange distribution. Sometimes there is only the northern crest. Sometimes there is only the southern crest. But this time there was a vertical bar that was dividing this or connecting the northern and the southern crest. I will tell you why it happens. These are the 5 points I'm going to be talking about. By the way, LISN is the network starting in 2007. We started with the MRI grant from the National Science Foundation that was able to put not only GPS receivers, no, but also magnetometers and also Viper ionosomes. So you have three instruments, which I hope that you realize that these are useful tools in order to fully diagnose what's going on. Well, let's go to the next slide. So I don't want to just mention point 3 here is we're in the transition going from LISN to forward, which is a data-driven forecasting system, that we want to do. So point 4 and point 5 are two investigations that I'm presently doing. Okay, on the left, you'll see these white dots, Jicamarca, Puerto Maldonado, Tupiza, and Tucumán. This is the way that we started with 4 Viper ionosomes. These are ionosomes, which are fully programmable, very sophisticated hardware. You can really program any kind of distribution that you want, a set of pulses, etc. But unfortunately, at the present time, we have only 2. We have Jicamarca and Tucumán, which is under the southern crest of the anomaly. We want to put something in the northern crest, and I'm going to be showing some slides about the one that we want to put in the northern crest, which is in Colombia, South America. Besides, in that graph on the left, you can see some red dots. These red dots, what it means, these are oblique sounding receivers. What happens is when you transmit with a ionosome, the field of view is large, it's like 60 degrees. So the energy, I mean, the electromagnetic waves goes to everywhere. You can, even if you are 1,000 kilometers away and you have a receiver, which is synchronized to your ionosome, you can receive echoes. Of course, the echoes are from the middle point, but that's useful because you can get very inexpensive systems now. If you use USRPs and you get a good synchronization with your digisonde or ionosome, and then you can get another measuring system. No? So we have four. One is in Piura, no, and the others are close to Lima. But anyway, no, we can. This is also another tool that has become available in the last years. No? Oh, here we say the red dots. Now, in the middle, we have magnetometers. No, you can see, and you probably are familiar with this magnetometer in Piura, also in Jicamarca. We have now another one here in the center of Peru, the city that is called Tarapoto, no, that is exactly above Jicamarca, or due north of Jicamarca. And what do we use this? Well, if you have a pair of magnetometers, you can get the current associated with the electrojet. So you subtract the edge component, and then boom, you have this current which can be associated with electric fields. So this is very useful to have, no, and also it's very inexpensive system, and it always works. It can be deployed once, and then you have internet, you have your data on real time. Here on the right, the blue circles are the receivers that belong to LISN. We have not deployed all of them. Actually, we have a grant from FOSR in order to deploy 34 GNSS receivers. These are Septentius, but we haven't finished deploying all of them. But some of them are already functioning, and you can see the data in our website, which I'm going to be talking later. Now, the red dots, what's the red dots? These are GPS receivers and GNSS receivers, which are being installed in South America for most of them for more than 10 years, and they continually operate. So we get also data from those, and we also process the data. So we have a good coverage. Of course, it's not perfect, yeah, but it's good. No, so we can go up to Mexico. Of course, there is more receivers in North America that sometimes we use when we do a magnetic storm analysis. Okay, so this is now going to northern Colombia, and look the map that is to your right. You see a city with the name Tunja. Well, Tunja is a small city, but it's a college city. No? And then we have an agreement with this university, UPTC, and they have a big land which they use to teach the students agriculture. No? And they have a lot of space. So what we did, we asked for permission to the rector of the university, and then we built a shelter. And the shelter is already built, as you can see in the middle. We are putting now electricity, no, to the shelter, no, and we can hold. We are going to house the system there, no, and this digisonde system is not very big, so we have actually a space for more instruments if we want to deploy. We will have a Viper ionosphere here, which is already in Colombia, no, and then we'll have a internet, no, and probably GNSS receiver. In the future, of course, we want to go back to Puerto Maldonado, no, and we want to go also to the southern part of Argentina, as you can see in that plot on your right. Well, but now let me go back to LISN. No, LISN has been operated, as I said, we have data from 2008, no, and we have real-time data. I think I'm putting here, I don't see it, but I think I have the web page where you can go and you can see. If you go to the web page, the first thing that you are going to see is this part that is at the top. Just click on real time, and then you'll see our real-time data. First, you are going to see profiles, but later, but if you scroll down, you are going to see these kind of plots for the current day. Actually, this is yesterday, so I downloaded yesterday, no, at the end of the UT day, no, and this is April 29, April 28 for Jicamarca and Tucumán. So these two are working. So you go to the web page, you'll see these plots that are coming on real time, no. So we get the ionograms, we translate these two densities, No, and we plotted here. So actually, we are running Artist in real time. No, so probably you are familiar with Artist. What you have at the bottom is the record of our forestation. And the forestation, as I say, Jicamarca, Puerto Maldonado. Jicamarca is still operating. The same for Tucumán, which is the third one. And then the other one, the other two, Puerto Maldonado, stopped taking data because of lightning. No, even though we had some protection, but its lightning was very close to the site, and then we lost part of the system. No, and then in Tupiza, unfortunately, we have some political problems. No, and then we left Bolivia. No, but we hope to come back in the future. This is data from our oblique sounder receivers, and you can see that these are the typical patterns that we have, these modulations due to gravity waves, and sometimes we can use it in order to detect even the motion of these TIDs or gravity waves, which are produced in the TIDs. Now, for example, here, these are two consecutive plots taken from Ayacucho, which is like 400 kilometers from Lima, and you see that, and then later on, is seen at Jicamarca. So this was a TID or gravity wave, which was producing this TID that was moving westward, from the interior of Peru toward the coast, to Jicamarca. But of course, we can also get the density profiles from this, even there is oblique receivers, and look, here for the oblique receivers, we don't need a transmitter, just a receiver, which can be done with a USRP, and these were done with USRP 200, but we are ready to move to the USRP 300s. Well, this is switching now to another project, and this is about the TEC depletions. TEC depletions are produced by plasma bubbles. So when the plasma bubble crosses the field of view, the line of sight of these GPR receivers, is going to see a decrease in the TEC. Why? Because this bubble, because this hole that is the main part of the plasma bubble. So, for example, here the plot in the middle, you can see this huge depletion, and this is 20 TEC units. So here is at least 10 TEC units decrease in TEC. There is a small ones, and here the program detects the beginning at the end of these TEC depletions, which I call. But we do further processing, and the further processing is trying to find the envelope of this, the upper part of this, in order to get the depletion, the depleted part, which is what we want. And you can see after doing 2 iterations only, we can do more. And actually, I advise to do 3 or 4 iterations, and then we get the depleted part. Now the scale is different, but this is at least 10 TC units, and sometimes even more than that. So you can see how they are detected. They detect all of them. Now the stations are very close, are here in Ecuador, and that's why they look almost the same, But there are good things that can be extracted from this. I'm not talking still the tomography. I mean, we can think even also later on tomography. But let me go to the next. Yeah. Okay. Yeah. Okay. This slide actually shows what we do. Yeah. So based on these plots, the one I showed before, we decided, okay, what about if we try to measure the velocity of this, how these plasma bubbles move? So this is a project that I thought for quite a time, So what other parameters can be measured? So what I did was just to plot TC from the receivers, which are close to the magnetic equator. Why? plus minus 7 degrees from the magnetic equator. Because these plasma bubbles, when they start rising, they form branches, and then they become like a tree, very sophisticated. But when they are low altitudes, they are not. They are just a tube, like a tube aligned with a field line, no? And this, they don't change it much, no? So, and that's why we restrict in latitude, so we can have only low latitude part of this. Yeah? And TEC, GPR receivers, because of the strange shape that they have, they have a 55 degrees declination. So and it's variable actually for all the other satellites. They can be very, very sophisticated and mixed images. But if you restrict to plus minus 7 degrees, you see just the central part of the bubble. So now we have 25 stations going from the west of South America to the east of South America. And this scale, number from 25 to 1, becomes longitude, because I am plotting this as a function of longitude. Okay, so, and this is time.
Okay, home
So this gives me the
address
progression, the
is
evolution actually of the TEC depletion. So we can get a lifetime, we can get scintillations with our receivers. Between these 25 receivers, only 4 of them belong to LISN, and we measure scintillation. The other receivers, unfortunately, even that they could measure scintillation, they don't report scintillations. What was interesting of this plot is that the scintillations start increasing. This is the S4 index, and you see how it increases. This is completely unusual. Even went to 1. S4 index became 1, L-band. Now, this was new because usually they are very constant, and they keep the same value during the night. Of course, at the end of the night, they decrease. But this was completely the opposite. Look, this bubble, for example, it grows, it keeps growing, sort of splits in several, and then at the end, it's decreasing. But that's when the scintillation is the largest. Okay, another point that I want to make is that we can measure the velocities also. How? We do the cross correlation between adjacent receivers. And even you can keep going for 3 or 4 receivers and find the velocity. And then you sort of find the average, or you do some fitting there, and you can get the velocity. So the velocity, you can see that is sort of increasing and then decreasing. Also decreasing with the latitude, because usually the bubbles, they arch. The velocity and the edges of the bubble are smaller than at the center of the bubble. And that's why they have this concave form, if you look at it in 3 dimensions.
So Dr. Cesar, so this, sorry,
Yes.
the time shift of the bubbles, are they as a result of that the bubbles are moving, or the time zone of the station?
Well, it's the plasma drift. The plasma is drifting. And during the night, the plasma drifts from west to east. And usually is 100 meters per second. So that's the motion of the main part of the motion of the bubbles. But the bubbles itself, they have also electric fields. Inside the bubble, you have electric field because there is a depletion there. And that electric field, sometimes it pushes the plasma even further. Yeah, so the bubbles usually go a little faster, like 10 meters faster than the plasma, the background plasma. But they are shifting together.
And that is what is calculated at in this plot here, in the bottom plot.
Yes. Yeah, that's what. So we usually say is the depletion motion, but it's related to the plasma drift.
Okay.
Very close. Yeah, but and sometimes it's actually the same. And now Jicamarca has a measure to they can continue routinely measure the drift, so we can start comparing those drifts, the bubble motion with the other, so which is very, very, very good for us. Okay, so let me show you some statistics. These statistics are for the whole year. This is 2016 and 2017. This is the Peruvian sector, which is here. This is the field line, which I'm using, no, for which I call Peru sector. And this is the Brazilian sector. These are field lines that really, this is only 2 degrees, no, crossing the equator here, 2 degrees. No, these are the Brazilian that intersects the middle of Brazil. Now, if you do the comparison, if you do very wide comparison, no, between the Peru and the Brazil, there are quite differences. You start looking carefully. For example, in Brazil, you have scintillations almost every day. Every night you will have scintillations. Yeah, here it doesn't happen, but in average, you have almost every day. No, in Peru you don't have every day, and you can see here, and the same here. No, and actually, if you do a statistic, Peru becomes only 70%, and during these months, what we call the scintillation days or the plasma bubble season. No? Brazil has also a season which is shorter than the one in Peru, no, because it's at the end of May, yeah, excuse me, at the end of March, it's decaying, and then you have the summer with the northern hemisphere summer with no bubbles. So these statistical plots have been done by calculating the plasma bubbles for every day for all these stations that we have, the 700 stations which are in South America and Central America. So there is a lot of processing that has been done. We analyze all the stations that we can get. And the same, and that's why it goes up to 20, sometimes 30 degrees. When there is magnetic activity like this day, of course, it goes to higher altitudes as we see, but not for all the storms, some of the storms. Okay, here it really continues with the statistics, and this is for 6 different years: 2012, 13, 16, which I showed before, 17, 18, and 19. Yeah. So these are more or less years of solar minimum, and you can see that the amount of depletions are diminishing. No, so you have also a solar cycle dependence of the scintillation activity. No, so instead of 70%, when you really are in solar minimum, it becomes like 60%. So these are statistics, of course. We would like to do much more. No? These are statistics for 2016. It's still the Peruvian sector and the Brazilian sector. This is practically the same plot I showed before. But here, I'm showing the S4 index. And the S4 index also follows the same pattern for Brazil almost every day. And then for Peru, not every day. So as it should, no? Because scintillations go with the plasma bubbles. We also make a plot of the velocities, and here there is a new feature that we observe. In Peru, always moves eastward, but in the Brazil, not always move eastward. You have sometimes a reversal of the velocity, no? And sometimes they move back westward. Why is that? That's a question that at this moment I don't know how to answer, but it has to do with electrodynamics also, because those are the ones that you control. So you have more reversal of this drift in the Brazilian part and the Peruvian part. So why so different? No, if it is in the same continent, yeah, it should be more or less the same. No, but there are differences, and for example, is the location of the magnetic equator, which is quite different in Peru and also in Brazil. In Peru, it's south of minus 12 degrees south of the geographic equator. In Brazil, reverses. And also the declination. In one is north, in the other is tilted to the west. Okay, so here we change gears. And now this is the new project we have submitted to NSF for approval. No, what we want to do is not only the nowcasting, which we are doing now. No, we are presenting in real time what we observe, but we want to do the forecast. And forecast what? Plasma bubbles. Not only in Peru, not only in Jicamarca, but we want to do the forecast in the whole South America. So we started in very modest way. We try to forecast TC over one location, and that location is Bogota. So we, myself and a student from UTD, we got the data for the whole solar cycle over Bogota and try to do the forecast. Just to limit the amount of processing that we want to do, what we did was first try to rank the importance of the different inputs to the ionosphere. So we used like 36 different variables: the solar flux, the Lyman alpha, the KP index, DST index. So all these parameters, 36 parameters, where we try to find the importance of this. And then in our forecast, use the most important one, use only 5 or 6. And that really simplifies the amount of computation that we want to do. In order to do this, to rank and find this distribution, all these variables, and here we are putting variables from the magnetosphere and the ionosphere. We didn't put inputs from the atmosphere, but that's the next step. Okay, so, and we use the decision trees, which is part of a random forest, and then we found these variables. As you see, F10.7 is the most important parameter, and that's what we use next in order to do. So we do a regression neural network, recurrent neural network analysis, with all these inputs that we have. So this 11 years was divided in 10 years to do the training of the decision trees, the random forest. And then we use for test, we use the last year to do the forecast. And we found that in 30 minutes, it was a very good result. It got it like 99% accuracy in our predictions. Of course, when we go to 1 hour, 3 hours, 5 hours, it starts decreasing. But even 5 hours later, the TEC was only 95% which is a good result. So we want to repeat this analysis, not only for one station, but a line of stations. Maybe they go to 2-dimensional and do the whole continent and do other parameters the same, like f of 2, the altitude of the F layer. So all these parameters that have been measured with the ionosome can also be done using this same approximation. And this is what we propose. We propose to National Science Foundation to do this forward. So LISN will become forward, and we will use this distributed observatory, in order to do the forecast. Different to other kind of forecasts, which are sometimes based on models, our forecast is really based on data that we have taken since 2008. So we have a huge collection of TEC values since 2008. We have a data from the Vipers that started in 2010. And then, of course, we are going to self-correct in the sense that we will be measuring also. So we will have the nowcast, and we will compare with our predictions. So we will know in real time how are we doing and why sometimes we have errors. For example, if we predict bubbles, there are no bubbles. Why? So maybe it's TIDs, and we have planned also to do the real-time detection of TIDs, which, I'm not going to address that here, but it's also something that we have spent a lot of time. Okay, so here we go to another point. Yeah, so this is one of the investigation, and I think I showed this plot before. No, this is the plasma bubbles observed on February 12, 2016. No, and that's the one that I told you about. Here we have scintillation increasing through the continent. So when it gets to Brazil, it became very large. No, uh, uh, and we didn't know why. So we thought about analyzing this. The first thing to see is, well, how is the TEC distribution? And this is what you see here on your right. This is the TEC distribution of that day. It looks very strange, no, because there is a connection, but actually this is a result that I have changed the range of this. Look, this is the same plot as the one you have here in the extreme left. No? Here, no, there is no this branch, but if you change the range of this, the scale of this plot, you'll get this, no, you'll get this branch. Yeah, this is the only thing I've done. No, play with the ranges and with the scale of the colors and then. Well, let me show you the movie, no? and the and you are going to see how these things evolve, no, and how TEC is changing. So here we have the northern hemisphere, and we are crest, and we are losing part of the southern hemisphere crest. And here is the part that really connects the northern hemisphere with the southern hemisphere. And it seems that this is like a loop that is moving, everything is moving to the east. So very strange, no? Very unusual. I think only a few times. So the first thing was to see, well, this is happening, this magnetic activity maybe, or maybe something else. Well, it happens that magnetic activity was quiet, so I don't think it have a role in that. No, and here you can see just three stills frames from the movie. No, and you see how it changes. No, from sort of connection between the north and the south. No, to a loop that is moving east. But looking carefully, we realized that there was a sudden extra warming event during those days, which is starting on February 8th. So, and then we realized that, yes, there is a connection of this increase in the scintillation, no, inside the bubbles due to this sudden extra warming event, no. So sometimes it has been reported that maybe SSW brings more scintillations, but in other cases, people have observed, no, it doesn't bring more scintillation, it brings less scintillations, or sometimes it obliterates scintillations. Well, so we want to really address this point. What happens with the bubbles and with scintillation during extra warming events? So that was a good question. No, you are going to find also similar problems in Africa. No, so one of the processes that really affect and produce this variability during SSW events is the lunar tide. And the lunar tide, it has a phase shift every day. This is a plot from Bella Fayer, no, produced in 2010. Actually, this is data from two magnetometers, one at Jicamarca and the other in Piura. And what he's plotting is a number proportional to the currents in the aurora electrojet. And you can see that there is a delay every day. No, this is from December 30 to January 12 or 13, and you see a daily phase shift that is produced by this. And then in our data, we have also Jicamarca and Piura, no? And we see also, but it didn't last many days. It lasts only like 6 or 7 days. Why? Well, there was a magnetic storm coming later, but it seemed that everything changed with this magnetic storm. But during these days, and during the day I presented, February 12th, we have the sudden extra warming event modifying, and in the lunar tide, modifying the electrodynamics. And that produces that So this is another plot. Actually, here I subtract the TEC. No, you can see this is just a latitudinal profile, no, for 24 hours. So this is the average for the whole month of February. I subtract that from every day, and you see that there is also a pattern, the same pattern that delays like 1 hour every day. So, and then look into the TEC profiles. For example, this is longitude 79 degrees west, 70 degrees, 60 degrees, and 51 degrees west. And how the asymmetry of the anomaly is changing. So sort of you observe also a change though in the whole configuration of the anomaly. But if you look at these profiles, you can see more or less what's happening. Here, for example, on the west, in the Peruvian part, you see that there is another crest, a very weak southern crest. But the things are changing through the continent. And then you have the southern crest, a very weak northern crest. The whole thing changes. The asymmetry of the anomaly changes. Well, you can say also the declination. But remember, in Peru, it follows the geographic latitude. It follows it's a straight north. Of course, during the night, it decreases and becomes. So what I think is happening is that the wind is changing. The meridional wind is changing. And that produces an increase in the, and also with the gradients produced by the plasma bubbles. It produces another component, and then sort of onsets another instability at the borders of the bubbles, like U, the velocity dot delta N produced by the bubbles when it's less than 0, and then you have a wind gradient instability. It could be just the gradient of the meridional wind, actually, the gradient of the meridional wind dot delta N, which becomes less than 0 in one of the bubbles, in one of the walls of the bubble. This has been published 2 years ago, and this is the reference if you want to follow that. Well, now let me follow to the last point. I think I should spend only 5 minutes here. This is the N1K irregularities, and probably this is the first time that you are going to be looking to this data. But let me explain. This is something I started actually when I was a student at UT Dallas. Sometimes, you have different kind of irregularities. Plasma bubbles happen most of the days, but sometimes you don't have plasma bubbles, but there are other irregularities that happen. It happens like 10% of the time, more or less in average, but they are still, we need to study. We would like to know what's going on, what's produced them, and that's the purpose of this project. N1K means near 1 kilometer irregularities. It used to be called bottom-side sinusoids, but here we are calling now N1K. Look, these are the 3 passes of the ROCSAT satellite, and these are the passes. One is away from Cajamarca, and the other one is very close to Cajamarca, and the other is practically on the other side. And this is what we observe, the density. The density here is practically constant, here in this part, so nothing was observed. But here is when we start observing a very thick trace, and then some bubbles at the end. Okay, yeah, so maybe that's that's okay, bubbles occur, but the strange thing was that there was nothing here, something, a thick trace. The next orbit is this, and there is also a thick trace. By the way, here this other plot of the small pluses is the roughness parameter. The roughness parameter there is the standard deviation divided by the mean value multiplied by 100. This is what I plot here. And we use that parameter in order to distinguish when we have No? Of course, when there are bubbles, it goes to practically 100%. But when there is the other thing, this N1K irregularities, it becomes like 10, 15, no, percent. Now, the next thing to see is to expand this, to expand the scales, no, and see what's going on. So it looks like a monochromatic wave, and this is why we call near 1 kilometer. And actually, you make a spectral analysis, this is about 2 kilometers. So it varies from 500 meters to 2 kilometers. All the events are different, and this frequency is always there, but it looks like a sinusoid. Of course, there is a decrease. Now, what's important to say here is that this green part of the trace is when we observe the N1K irregularities. And we plotted in green just to indicate that it's always very close to the magnetic equator. But look, it's in the other side of the magnetic equator. It's in the southern side. On the northern side, it seems that there is nothing. Completely different to plasma bubbles, which are always symmetric with respect to the equator. No? So you see what's in the north is practically the same what's at the south. Okay, so fortunately, during that observation, which was in 2002, we have the digisonde and the Jicamarca operating. So we have another diagnostic of what's going on. And then there was a very unusual pattern. And that pattern was that the density increased. And it's very unusual because it went up almost to 700 kilometers. It doesn't go quite often to 700 kilometers. Now, that was good because ROCSAT was flying at 650 kilometers. So ROCSAT was at the bottom side, and the F layer, the peak of the F layer was higher up. And then the other thing that really we didn't know until we have these GPS receivers, and now we make a plot of 24 hours, there is only another crest, no southern crest. There were some scintillations, even though there was no bubbles, but there were scintillations. They were weak, and these are UHF scintillations, but that's important. And now, another thing that really we knew from before is that when we have these near 1K irregularities, we see frequency spread F. And the reason is, and now we know, because this variability in density that we observe translate into this variability and frequency that we see here. So looking to these profiles given by the digisonde, we can more or less relate what's the density variability in altitude. So we should be able to compute that. So, and you can see this is the profile. So the peak probably is very small, but sort of increases to the middle in the bottom side and then decreases at the end. But we have later a CNOFS satellites, as you know, and this satellite was equatorial, as you can see here in these passing very close to the equator. And now, this is a pass, and this is the density that was recorded. Look, this part looks like the density profile that has been rotated 90 degrees. So what's going on here? Well, the satellite is going to a region, like the previous example, the region of the ionosphere that is moving up. And that's why even the satellite is flying at the same altitude, but it's crossing different regions of the bottom side. So the bottom side is all the time higher and higher, and the satellite is going. And here, at this point, it's 10 to the 3 only. So the satellite is getting to the bottom side. That's the minimum that the satellite can measure, 10 to the 3 density. So the whole ionosphere, and you can see the velocity here, the vertical velocity in red, the whole ionosphere moved up. This is the next orbit, and you can see a small valley No? And this is now the roughness parameter in blue. No? So increases to 10%, and you have the valley. You have the confirmation that the region has moved up because of this large velocity, 50 meters per second. So all this is sort of very important. This is another pass, just 2 days later. And you can see there is always a valley, no, because the layer has moved up, no, and you can see that persists for the next orbit. Now, this is again, the density profile measures on that day. The ionosphere goes to 550 kilometers. We reduce the velocity. There is also the asymmetry of the anomaly. No, only northern crest and no southern crest. And you see the frequency spread F for all these times. Here is the expanded view because CNOFS measure up to 1 kilohertz. It was measured the density up to 1 kilohertz, and you see the peak is very close to 1 kilometer. So, okay, so this is confirmation. Okay, these are near 1 kilometer irregularities. Now, the most important thing here, sort of summarize this. The ionosphere moves up. Now, if the ionosphere is at higher altitude, it should be more unstable to the Rayleigh-Taylor instability. However, during this day, it was not. The previous day showed some bubbles, actually, but to the east. Here, there is no bubbles, and the first case with ROCSAT data, there was also no bubbles. So that's very significant. Now, all these events, here we have 4 days, almost consecutive days, that shows the big asymmetry also in the TEC. TEC just with one crest. Now, by the way, actually I confirm this was also a sudden strato warming event. Yes, there was a sudden strato warming event during this day, and that's the important thing. Yeah, but I don't think that we need a sudden strato warming event in order to have near 1 kilometer irregularities. It can be done also in the other ways. Yeah, I'm very close to the end. I'm sorry for extending this, but now going to the theory, I believe there is an instability going on. So we study different instabilities, and the first to study was the temperature gradient instability, and the reason is that when you move the layer up, there is adiabatic cooling. So TI, probably also TE, decreases. If the temperature decreases when the density is increasing, you have the setup for the temperature gradient instability. So we analyzed the possibility of this. This is another day when Cajamarca was observing, yeah, but actually we didn't observe near 1 kilometer irregularities this day. Yeah, look, this happened actually hours before. No? So, and the gradient in the temperature, the blue is the temperature, the ion temperature, and the red is the density. So they are going in opposite directions. No? One is decreasing due to this adiabatic cooling of the ionosphere that it moved, really, look, it moved up to 600 kilometers altitude. No? So decrease adiabatic cooling. And so we put the formula for the growth rate under these circumstances, and we got 100 minutes. So that's too large, really, to be effective. So maybe something else going on. No? And this is the one before the last. So what happens is this is a schematic of what's going on. It's a section of the ionosphere that is moving up. So it's like this rectangle in dark gray that move up. So, and then here at the bottom, it creates like a hole, like a bubble. So in that bubble, you have an electric field, no, in this direction. But in the other part, gravity is going to create this electric field in the other direction. Now the velocity that produces this electric field is one is in green, moving down, and here is the one like a bubble moving upward. So this is like a compression doing that. And I believe that is creating some kind of a stability of the large scales. So the large scale become stable, no? And only the 1 kilometer irregularities and the shorter scales, they are unstable and they evolve. So this is more or less what I'm investigating right now. No, I did the numerical calculation of this. No, and I hope the next time I will report my results. But I want to summarize just this last part. I think the near 1 kilometer irregularities are different, completely different to plasma bubbles. They are not bottom type or bottom side layers. No, they are associated with these frequency type ionograms. No, they don't need plasma bubbles in order to develop. No, actually, we don't know at this moment how often they occur. The only thing I notice is that during solar max, there are more events, solar medium. Okay, thank you. This is all. Thank you very much.
Thank you, Dr. Cesar. Wonderful. Thank you for the nice presentation. I think this is a very good way to leverage multiple instruments, ground-based and satellite-based or space-based instruments. Yeah, this is fantastic. And the floor is open if you have any question. I think there is a question for you in the chat box, Dr. Cesar, if you want to. Let me see.
Yeah, how do I go to the chat box? Maybe you can read the questions.
Bruno, is that Bruno? Yeah, this is the floor is open. I want people to participate in this. I also have a hand raise. Mr. Dr. Emmanuel, please have the floor. Dr. Emmanuel or Dr. Bruno, you can ask your question.
Yes, please. I don't see the button for the.
Yeah, I actually want people to talk.
Yeah, okay.
We want to
Hello,
talk.
Doctor. Can you hear me?
Go ahead.
Dr. Jana? Yes, Professor. Thank you the for the presentation. My name is Bruno. I'm not yet there in at the status of the PhD, but we are working and are dreaming. So as you made the presentation, I saw that from the South American stations, we are basically handling only one type of scintillation. I have been doing some reading from Ugandan concepts, and I see the Ugandan researchers saying that within the East African region, they are experiencing both the phase and the amplitude scintillation. And I expected that the South American stations should also have the same because we are within the equatorial ionization region. It is from that basis that my question has stemmed. Am I right to say that the South American stations basically have only one type of scintillation or something else is happening? Please some light on that. Thank you very much.
Yeah, let me see if I understand your question. Is if when we have these events, we have amplitude scintillation and phase scintillations, or we have just one of them? No, I think that's your question. No, well, we should have both of them. Yeah, we measure actually amplitude and phase scintillations. Most of the time, I don't show it. No, and at the equator, they should be more or less comparable. I mean, if one increases, the other should increase too. No, so but I haven't checked that, but that's a good question. I think I should check. What I expect is that if I see this large amplitude scintillation, I should observe also this large phase scintillation.
Yeah, Dr. Cesar, you can stop sharing your screen.
Yes.
Yeah, that will make you to see the chat box maybe.
Okay.
So,
Okay.
uh, I think I also like the part of the disappearance of the AIA in time, like, and you said sudden stratospheric warming is the cause of that.
Yeah, the anomaly. Yes. Yeah,
Yes.
this motion of the anomaly.
The
Yeah. Yeah.
disappearance. It disappears from the west to east. You start
Right.
seeing those
Right.
disappearance, and then at the crest, the northern crest remains, but the southern crest disappears in time. Is that
Right.
Do you have any explanation about the mechanism that could cause that from sudden stratospheric warming?
Yeah. I think is the my personal opinion, no, is that the lunar tide that it changes the whole electrodynamics. The lunar tide becomes like 3 times what it usually is. No, during normal conditions, it's very small. It doesn't make too much changes. But and then suddenly, because of this sudden extra warming event, it becomes like 3 times what it used to be. Yeah. So and then the whole electrodynamics is changing. And then what is changing is the meridional wind. So this changing in the meridional wind, no, that makes the whole thing move. No? And that's my view. But you are right. It has to be a numerical modeling, AMI tree or another model. No, maybe also related with the atmosphere. No, even the lower atmosphere. No, and then with that, I think that probably we can know more exactly what's going on. But I think it's the meridional wind that is changing. No, and also some changes in the zonal wind.
Oh yeah, thank you for that explanation. Mr. Ahmed wants to talk, but I think he's having situation with the mute or unmute of mic. I can only ask you to unmute. I cannot unmute you. So I've done that.
Well, now I can see the chat. Let me see.
I think, yeah, if you can unmute yourself, Dr. Mohammed Ahmed, you can ask your question. I think I also have Dr. Emmanuel. Do you want to ask your question? Ask the question now. We can unmute. I think it's possible to unmute yourself if you want to. People are having challenges.
It seems that you have to do it from your end. Jonah,
I'm
I
not
think this.
sure because I'm trying. Okay, let me make them co-hosts if that will help. So I'm making them co-hosts. So try to unmute yourself again. I just make you a co-host. Maybe that helps. Or you can type your question in the chat and Dr. Cesar can see the chat now. So it's also perfect. In the meantime, I will just thank everybody for their attention. And okay, so, okay, let me try to share my screen. So I'll try to share my screen. If you want to ask and you can ask a question, please interrupt me anytime. I'm okay with that. And if you can type your question, Dr. Cesar will see it and answer it. So we have a lineup of speakers, and Dr. Cesar has to swipe with Dr. Dr. Keats for this month because there was a conflict with Dr. Keats' an meeting. Another meeting he's having at one country. I don't remember. So our next meeting is going to be on May 28th, and we're going to have Dr. Kit Grove from Boston College. And I think most of us know Dr. Kit Groves, and he has worked a lot or put a lot of instruments on the African continent, and he knows a little bit about the dynamics of the instrumentation, how it is. It's going to give us a lot of information on what they are doing, their efforts on ground-based instrument over Africa, and some science results that he has to show. And again, I want to thank Dr. Cesar for showing us those interesting results. Though all of those results mostly are from South Africa, and we would like to start having
South America.
similar, sorry,
South America.
South America, sorry. I wish, right? But South Africa is having very reasonable instruments. So ground-based instrument over South America uh,
Mhm.
or South Africa is really good. So, but at the equatorial region, we have empty region of when you talk about ground-based instruments, and that is the focus of
Mhm.
meeting. So, thank you
Mhm.
very much for highlighting those results. Very fantastic results over South America. I think, do we have a
Mhm.
question for you, Dr. Cesar, in the chat box?
Oh,
So
he says, what's the role of N1K irregularities in the presence of magnetic storms on the characteristics of plasma bubbles? Uh,
that's from
well,
Dr.
it could happen during magnetic storms. Yeah. And sometimes I seen also N1K irregularities inside the bubbles. No? So what happens is that the bubbles become very structured, very structured. So it's like the 1K irregularities grow even bigger. It becomes like a 50% inside the bubbles. Yeah. So the bubbles sometimes there are like holes, but if you have both of them at the same time, no, or the bubbles get contaminated with N1K irregularities, this becomes completely structured. No? So that's what I'm saying. There are not many cases actually. No? And the last question, is there a work for validation IRI over South America, especially available of instruments? I don't know about that. I don't know. Yeah, I wish I could do more work with IRI, but I don't have the time. But uh, if anybody has the IRI model, I mean that's something worth doing. No, they can validate with all these Vipers ionosphere data that we have. No, so you are welcome. You're welcome. We can give you the data. Yeah, so if anybody wants to do that.
Yeah, I think Dr. Osai Taiwo did some work on HRI, but I think it's over Brazil. So maybe we don't
Yeah,
have time
okay.
for that discussion. Maybe sometimes Dr. Taiwo Osai can come and talk about his our work on that. I think he did a PhD on that. So maybe
Yes,
one of our meeting we will invite her to give it.
yes, yes, yes. Yes, yes. Yeah, but it should do also with Peru. I mean, yeah, I'm sure that Brazil is very well covered, but
Mhm.
as you can see, there is some differences between Brazil and Peru. No? It's worthwhile somebody doing this.
Right, right. Yeah, I think there is a final question there for you. I think it's about
Is N1K a common irregularity within the equatorial ionosphere or just in the South American sector? That's a good question. Actually, I have seen it in other parts of the world. So I imagine also you could see also that in Africa, in India also. Satellites are very good for that. No, I haven't looked to all the data from CNOFS, but CNOFS is a good satellite to do that kind of work, and you are going to find almost anywhere in the world. No, so that happens. Maybe there is a preference in South America because of this combination of the inclinations, no, and the magnetic field lines, no. So, but I've seen it a lot in India and Africa.
Excellent, excellent. I think that is all we have the time to take. We don't want to keep people waiting. I don't have the time to take the roundtable discussion about meeting people this week. If we have
Mm,
anybody that is new today, we will welcome you in our next
yeah,
meeting on
sure.
May 28th.
Yes,
And we are going to be having a wonderful presenter again. So hope we see you again in the next meeting. And I'm being,
yes, yes, of course.
yeah, Dr. Cesar, you are welcome always. This is your meeting. You know, you are part and parcel of this
Thank
campaign,
you.
right?
Yes,
So we're always happy to see you. So, and somebody is asking if we will drop the presentation. So, Dr. Cesar, are we allowed to share your presentation to the group?
yes, yes, of course, of course.
So if you
Yes.
can help me to drop your email, I think that will facilitate the sharing because I would like to share it to those people that attended the
Yeah,
only.
yeah,
We have
yeah.
about 200 people that are member of CONGA.
Oh,
And
wow.
because of
Yeah.
time constraint, we don't always have everybody present. So I don't
Mm,
know if it is the right thing to share with everybody or to just share with people that are present. Some of the presenter, they allow us to share with people that are present. So, and that is, their own policy. So if you can drop your email address, that would be wonderful. And I will share the presentation with you. We also have a YouTube, private YouTube that we put the video or audio presentation, so you can always visit there. Somebody told me that he was not able to access these videos because it is private. But okay, so I think we are going to be making it public so that everybody can access it. So if you miss the meeting, you can always check on that. This is a very
mm,
effective um, presentation, and you always expect that on Conga meeting. All our presentation are very educative. So if you miss it, don't worry. If you want to learn more about it, maybe you miss some things along the line, you can always see
mhm.
the video. So thank you again, Dr. Cesar. I think I have the emails coming up. So please put your emails and I will share the link with, the presentation with you. Dr. Cesar, could you
Yes,
send me
yes,
the presentation and I will share with the people?
yes, yes. If you want the slides, I can send it to you also.
Yeah, send me the slides, yes.
Yeah, maybe in two
By
groups
email.
because
I
yeah,
will
there are more
share.
than 25K or 25 mega, as you
Oh,
say.
okay. Yeah, you can share with me on Google Drive or something.
Okay,
All right, Dr. Cesar. Thank you, everybody. Thank you, Dr. Cesar, for the wonderful presentation. We enjoy every bit of it. Thank you.
thank you for the invitation. Thank you very much.
Sure. We'll see you next meeting,
Yeah,
28th
yes,
of May.
of
Thank
course.
you. Ready? So I'm going to close this.